start with something you can actually picture. Mount Everest, the tallest mountain on Earth. Now forget it, because by the end of this video, we're going to zoom out so far that Earth itself becomes a meaningless speck. Our entire solar system becomes too small to matter, and even our galaxy, home to hundreds of billions of stars, becomes just one tiny thread in something almost too vast to describe. Today we're not exploring a single object. We're climbing a ladder of scale, one rung at a time, until we reach the largest structures ever discovered in the observable universe. Let's start small. Mount Everest stands at roughly 8,849 meters above sea level, genuinely massive by human standards. But even on Earth, it's far from the biggest thing around. Measured from base to peak, Mauna Kea in Hawaii is actually taller than Everest at over 10,000 meters. Most of it just happens to be underwater. Then there's the Great Barrier Reef, a single living structure visible from space, stretching over 2,300 kilometers. Even the largest living organism on the planet isn't a whale or a tree. It's a single fungal network in Oregon spanning nearly 10 square kilometers underground. And all of this, every mountain, reef, and organism, exists on a planet that's about to look impossibly small. Zoom out to the solar system, and Earth's giants instantly become irrelevant. Jupiter alone could contain over 1,300 Earths inside its volume. But even Jupiter is dwarfed by the Sun. You could fit roughly 1.3 million Earths inside our own star, and the Sun is considered a fairly average, mid-sized star by cosmic standards. And average is doing a lot of work in that sentence, because some stars make the Sun look like Earth just made Everest look small. Scuti, one of the largest known stars by radius, is estimated to be over 1,700 times the radius of the Sun. If you placed Scuti at the center of our solar system, its outer surface would extend out past the orbit of Jupiter. Even a star as monstrous as Scuti is a rounding error compared to the structures that create stars in the first place. Take the Tarantula Nebula, a massive star-forming region roughly 170,000 light-years away. It spans nearly 1,800 light-years across, an area so large it contains, quite literally, tens of thousands of stars within a single cloud of gas and dust. To put 1,800 light-years into perspective, light, the fastest thing in the universe, would take 1,800 years just to cross from one side of this single nebula to the other. And this cloud isn't even one of the largest structures we're going to encounter today. It's still, in cosmic terms, a relatively local, contained object. Zoom out again, and even massive nebulae shrink to near invisibility. Our own galaxy, the Milky Way, spans roughly 100,000 to 200,000 light-years across and contains an estimated 100 to 400 billion stars. But the Milky Way isn't even close to the largest known galaxy. IC 1101, a supergiant elliptical galaxy, spans an estimated 4 million light-years across, roughly 40 times larger than the Milky Way, and potentially containing 100 trillion stars, compared to our galaxy's hundreds of billions. If IC 1101 replaced the Milky Way in our sky, it wouldn't just be visible. Depending on orientation, it could span a significant portion of the visible night sky as seen from Earth. Individual galaxies, even monstrous ones like IC 1101, aren't isolated. They cluster together under gravity into galaxy clusters and superclusters, structures that dwarf individual galaxies the same way galaxies dwarf individual stars. Our own Milky Way belongs to the Laniakea supercluster, a structure spanning roughly 520 million light-years and containing an estimated 100,000 galaxies. Laniakea is a Hawaiian word meaning immense heaven. An appropriate name, since discovering its true extent, mapped by researchers analyzing the motion of tens of thousands of galaxies in 2014, reveals that our entire galaxy is just one small part of a vastly larger gravitational structure than previously understood. Now we reach one of the largest structures ever confirmed to exist in the observable universe, the Hercules-Corona Borealis Great Wall, a massive concentration of galaxies discovered through gamma-ray burst mapping in 2013, estimated to span an almost incomprehensible 10 billion light-years across. For context, the entire observable universe is estimated to be about 93 billion light-years in diameter. That means this single structure spans roughly 1/10 of the entire observable universe's width. Some astronomers have actually questioned whether a structure this size should even be theoretically possible under current cosmological models, since it approaches the scale at which the universe is expected to look statistically uniform in every direction. This discovery remains an active, debated area of astrophysical research rather than fully settled science. Past structures like this, cosmologists generally believe the universe becomes statistically uniform at the largest scales, meaning no bigger objects, in the traditional sense, are expected to exist. The universe as a whole is either infinite or so vastly larger than the observable portion that the term largest object starts to lose clear meaning entirely. That's a strange place to end a journey about scale, not with a bigger number, but with the very concept of biggest beginning to break down entirely once you've traveled far enough. The part worth sitting with: everything we know, everything humanity has ever built, thought, or fought over has happened on a single planet, orbiting a fairly average star in a fairly ordinary galaxy, itself just one small thread inside a supercluster that is, itself, dwarfed by structures 100 times larger still. That's not a depressing thought, it's a genuinely useful one. It's a reminder of just how much room there still is left to explore, to learn, and to wonder about in a universe that keeps getting bigger every time we think we've finally found its edge. If this journey through scale blew your mind, subscribe to the channel and let me know in the comments, which one of these structures should we explore in more depth next?